including MEMS and NEMS, also their applications. He received his MSc Engineering and PhD degrees from IISc. The R&D work carried out by him resulted in the realization of several useful sensor devices and measurement systems. He has more than 120 papers published in leading international and national journals, conference proceedings, and invited articles in the encyclopedia. He has 6 patents to his credit. He is a referee or reviewer for several national and international journals in the area of sensors. He served as a member of the editorial review committee of the Journal of IEEE Transactions on Instrumentation and Measurement. Presently, he is a member of the editorial board for 2 other international journals in the area of sensors. Professor Rajanna was a visiting fellow of INSA, Indian National Science Academy, Japan Society for the Promotion of Science programs twice. Also, he was a visiting professor at Tohoku University, Japan. He served as a member of Technical Program Committee for IEEE International Conference on Sensors and chaired several sessions. Also, he served as a member of Steering Committee of the TPC for APCOT, which is the Asia Pacific Conference on Transducers and Micro Nanotechnology. Professor Rajanna also served as a member of the TPC for 11th Annual IEEE Conference on Nano and Micro-Engineered and Molecular Systems, held during 17th to 20th April 2016 at Japan. Sir is a member of the Board of Management of Defense Institute of Advanced Technology at Pune. He is also a member of the institutional body of NIMHANS, which is the National Institute of Mental Health and Neuroscience, since November 2018. Presently, he is also an expert advisory group of DSU. Professor Rajanna was elected as a Fellow of Instrument Society of India during 2015. He has guided several research students for PhD and master's degree, and I'm very proud to say I'm one of his PhD students. He has also successfully completed several sponsored projects from IISc, DBT, ISRO, DRDO, DAE, DOE, and MHAT. A warm welcome, sir. Over to you for your talk.
Thank you. One more.
Okay, Suresh.
Just yeah.
Switch on only.
It's on.
Yes,
okay,
yes.
okay. We can put it. This also should be.
Is on laser.
Pointer is on. Good morning to all once again, and I thank Dr. Vaishali for introducing me to this audience. In fact, I started my research activity in the area of vacuum, and later I, along with my students and collaborators, focused our work on the application of sensing and sensor development actually. So that's why for my today's talk, I chosen the title Recent Trends in Sensor Technology and our developmental activity on nanostructured materials-based sensor. Of late, we focused our activity on the realization sensors using a very versatile property of nanostructured materials. So this is the thing. I thought I will give a brief introduction, and then I will try to focus on some of the important sensor devices that we developed. And whatever I'm going to present is the hard work of my research student, as you mentioned. Okay, this is the general outline of what I plan to talk today. I will give a brief introduction to the topic, and then I will concentrate on some of the work that we have carried out on the realization of low-cost acoustic sensor, impact sensor. These are also very important type of sensor that are needed in several areas of science and engineering. Then MEMS-based sensors and actuators. These are also very important because everywhere miniaturization is taking place. So MEMS-based sensors are becoming very popular. So I will touch upon some of the work that we did on this, and then energy harvesting devices work that we have done in the recent past. Sorry. This thing is not. Which one? Oh, I understand. Okay. So I thought, since I'm from the Institute of Science, there are many youngsters out there. I thought I should show some of the views of the Indian Institute of Science campus. This is a aerial view of our campus. This is around 400 acres. It's a big campus, and at that time, Maharaja of Mysore donated this land. Now, this is the main building where this, and in front of that there is a Tata statue, and it is, and the earlier name was Tata Institute. Even today, people call it as Tata Institute, but the official name is Indian Institute of Science. There are many buildings. This is the earliest, the building that came up this thing. Of course, another view. This is the main building where even the main our register office, director's office, etc. is located. As I mentioned, the very multi-story buildings have come up nowadays, and we have more than 40 departments in the campus. In fact, many they used to ask, especially when we go abroad, etc. They used to say, "Your institute name is Indian Institute of Science. Is that only science departments are there?" But although I should mention that the name of our institute is Indian Institute of Science, we have almost all branches of science and engineering. This is the information of the students, because many may aspire to join after engineering or science, but Indian Institute of Science has all the branches of science and engineering. So this is the main building. I just thought I should show that those youngsters, they intend to come to the institute, may have a glimpse of what I am going to show. So I thought I will give a brief introduction. As I mentioned, I started my research activity in the area of vacuum and thin films. In fact, thin films find applications in many areas. The earliest application of thin films was in the area of optics. Then microelectronics also, in many ways, thin films are useful. Surface engineering, sensors, and so on. Coming to the optics, most of you might have done some optical experiments during your course in the first year of engineering or second year, where we come across the simplest optical device, beam splitter. Hope you might have heard about. It will split the single beam into two. It's the simplest optical device. What it does is a glass plate onto which a reflecting layer is coated. This layer normally is coated by thin film deposition process. So whenever the light falls onto this, part of the light get reflected, part of the light get transmitted. Depending on the thickness of the reflecting layer that you coat, you can now choose the intensity of the reflected component and as the transmitted component of the light that is getting falling onto the. Like that, there are many optical components that we can realize using thin films, laser mirrors, dichroic mirrors, and anti-reflecting coating that we use on camera lens, things like that. So then, of course, in the area of microelectronics, also thin films are useful in a big way. Surface engineering, corrosion resistance coatings, and etc. in mechanical engineering aspect. Sensor is another important area. Thin films are finding in application in a very big way. Especially in the recent years, application of thin films of sensors is becoming more popular because of several attractive features and versatilities. So the field of sensors is very diversified because we have a number of different fabrication technologies involved, number of parameters that need to be sensed, and number of problems that can be solved using suitably designed sensing devices. Interestingly, the various physical and chemical parameters that potentially be sensed can be grouped into 5 major groups. Let us say the parameter that we need to sense can be radiative parameters like light or X-rays. It can be chemical parameters like pH of a solution, humidity or a gas, or it can be a magnetic parameter. Sometimes the parameter that we need to measure can be a mechanical parameters like a pressure, flow, level, or vibration, or it can be a thermal parameter. In sensor technology, the basic operation what we do is the following. The parameter to be measured, we call it as a measurement. We convert it into electrical signal. Once it is converted into electrical signal, this can be modified, amplified, or transmitted this thing, it's whatever it is. The basic operation that we do is convert this measurement into an electrical signal. So for different type of measurement, you need different type of sensing material. It can be a piezoresistive, a piezoelectric, or a capacitance phenomena. Various phenomena are being used, and the material that we synthesize can be a simple thin film or a non-structured material, and like that. Similarly, if we look at the basic aspect of sensor, the input parameter that we need to sense in case of sensor is a non-electrical, but output parameter is electrical in nature. Similar way, in engineering aspect and other thing, in addition to sensor, we also hear about actuators. These are also very useful. In some of the engineering problem, we need both sensors and actuators together. So the basic difference between the sensor and the actuators is, in case of actuator, the input parameters is electrical, output parameters is non-electrical, like displacement, vibration, things like that. I just thought I should mention because many of the engineering students, they are interested not only in sensors but also as actuators. But I thought you should know what is the difference, basic difference between the sensors and the actuators. So, in thin film, deviation from the properties of the corresponding bulk materials arise because of small thickness and large surface to volume ratio and unique physical structure. In some cases, we need very highly arranged crystalline kind of material. In some cases, amorphous type of this thing. So, in thin films, we have the versatility to tailor the properties suitably, either making them highly crystalline or amorphous in nature. And there are a number of parameters which will influence the properties of the growing film. Most of these thin film depositions are prepared under vacuum environment. Of course, there are cases where thin film can be used without using a vacuum condition. In most of the thin film deposition processes, we use vacuum. So the properties of the film that we grow depends on the degree of vacuum, residual gas present in the chamber, vacuum chamber, the rate of deposition, whether we do the deposition very slow or fast, and surface condition with substrate. I should mention here, the substrate is a general terminology that we use in thin film. Because thin films, as the name says, they are very thin. They cannot support by themselves. So we need some supporting materials. So this supporting material, we call it as a substrate. Suppose if it is an optical component, it can be a glass plate. Sometimes it's a quartz. But in engineering applications, it can be a metal or a non-metal, or in mechanical engineering, like what I mentioned in frictionless ball bearings, etc., corrosion resistant, it can be a metal. But in electronics, it can be a silicon. So substrate is a very common terminology that we use. So the surface condition of the substrate also influence the property of the growing film, whether it is rough or smooth. Especially for optical applications like reflecting coating, etc., we need a very smooth surface, polished surface. Whereas in some cases, deliberately we make the surface rough. And substrate temperature. While growing the film, whether we maintain the substrate at room temperature or at higher temperature also decide the property of the film that we grow. These are some of the versatilities of thin film technology. And it is not only that the condition that we maintain for substrate during the growth process, but also even after the deposition of the film properties can also be modified after the deposition by post-deposition treatment. It can be simple heat treatment. One can also irradiate with ion beams. It will modify the properties. Sometimes people irradiate with a laser beam. It will modify. Also, it can be subjected to microwave plasma. These are all the possibilities that we can modify the property of the film even after the growth by the process called post-deposition treatments. So I just wanted to highlight this because thin film technology is a versatile technology, so that we can tailor the properties of the material suitably depending on the application, whether it is for optical, mechanical, or electrical application. So if I look at the literature, I mean the methods that are available for the preparation of thin film, we have a large variety of techniques. We can broadly classify them into physical vapor deposition or chemical method. Under the physical vapor deposition, we have mainly evaporation sputtering. There are sub groups like that. Similarly, chemical vapor deposition, we have electrodeposition, chemical vapor CVD, and other methods. Of course, if you do not have these deposition techniques require sometimes expensive equipment, but some cases now, if you do not have this instrumentation, you can still prepare thin film by simpler methods like simple dip coating, spinning, solution coating, spraying, or polymerization methods. I think these are the methods we teach for for the students over a semester, but I will not go into the details of this thing. Just to give an idea, what are all the techniques that are available, I just shown this. So this is the simplest evaporation technique. What we do is, we take the material to be deposited in the form of a filament or a boat, and this is a vacuum chamber. We remove the gas, create a vacuum as low as about 10 to the power minus 5 torr minus 6 torr. We heat the material. Material melts, come to the vapor state, and now it gets coated on the substrate. This is the simplest technique to prepare a thin film, vacuum evaporation. This is since we are heating by passing electric current through the source material, either a filament or a board, it is called resistive heating method. So this is the simplest method, but it has its own limitations. Just to give an idea how we prepare thin film, I just made this simple diagram. Similarly, this is a vacuum chamber system that we had in our lab. So there are many accessories like the resistive source, the vacuum pump, the chiller for cooling the diffusion pump, etc. I will not go in the details of this one. These are the internal details of this. The heating arrangement, thickness monitors, so many things. A Choron baffle for creating the vacuum in the chamber, vacuum pumps, etc. So many accessories that I will not go. Similar to evaporation, there is also a technique called sputtering. This is a schematic of the sputtering technique. It has its own advantages, especially if you need a very good adhesion for the film, etc. In mechanical engineering, other this thing, we go for sputtering. Of course, even for sensor development, etc. So in this case, instead of heating the material to come to the vapor state, what we do, material to be deposited is taken in the form of a target, and then we have the substrate on the lower side. We apply a potential between the target and the substrate, which is at a ground potential. Gas gets ionized. These ions go and hit the target and remove the target material, and the material get deposited. This is a very little sophisticated technique, and here, especially if you want to deposit expensive material like gold, platinum, things like that, there won't be any wastage of material. It also provides the flexibility to have good adhesion, etc. I think just to give a glimpse of what is sputtering, I have shown this. I will not go into the details. This is a complete system. What I shown in the earlier, this one is only a chamber part. There are many accessories like for creating the vacuum, we have a vacuum pump, diffusion pump, electrolyzer trap, rotary pump, vacuum gauges, power supply for applying a potential, so many other things. Those are interested in instrumentation. I think you can appreciate the various components that are involved in the preparation of this. So this is how the process of sputtering take place. We have a target which is at a negative potential, the substrate on which is at a ground potential. Whenever the ions they go and hit the target material gets removed and they settle down on the substrate. This is an atom and atom condensation process. Depending on the potential applied, the various sputtering process parameters, we can tailor the properties with the film get deposited on the substrate. So if you use a direct current with a 2 electrodes, it is called DC direct sputtering. There are various modifications of this. If you use a third electrode in order to improve the ionization process and the deposition rate, it is called triad sputtering. Most of the metals can be deposited by DC sputtering technique, but if you want to deposit insulating material, the versatile technique is RF sputtering, radio frequency supply that we use. I think I will not go into the details of this, but this is a simple schematics to show how the sputtering process takes place. And this is one of the earliest sputtering chamber that was made by my students in the laboratory. This is a chamber, this is a target, because whenever the ions they go hit the target, targets get heated. In order to keep it cool, you continuously circulate the cooling water. So this is a plasma that we see inside the chamber. Sometimes, especially for a short and metal deposition, glass chamber is okay. But if you are going to do RF sputtering and sputtering for a longer duration, this glass chamber is not ideal. We go for a metal chamber so that we can do the deposition. So it's just to give an idea how the plasma looks like, I have taken this slide. This is a metal chamber. So, sorry, the pointer is not working. Batteries. So this is a metal chamber, box type metal chamber. This was also made in our laboratory by our student. Lower side, what is shown is a pump, diffusion pump backed by a rotary pump. This is a RF power supply. This is a gas cylinder. Normally, the inert gas argon is used. Sometimes, in order to do the reactor sputtering, in addition to argon, we also use reactive gas like oxygen. Then it's called react sputtering. There are various versions of that. Okay, so with this brief introduction about what is thin film and how we prepare thin film, I will now go on to some of the type of the thin film based sensor that we developed in our laboratory. I thought I will consider this low cost piezoelectric thin film based acoustic sensor. In fact, acoustic sensors are an important link in sound reproduction and communication system. Application areas of acoustic sensors include consumer products, space. They are also useful in space, medical, and industrial process. And in fact, human ear is a natural acoustic transducer with tolerance to wide amplitude variations. However, either it fails or becomes apparently impossible to use in hazardous and radiation environments and remote areas. Therefore, there is an increasing interest to develop acoustic sensor which can be used to sense high intensity sound and can be employed in adverse environmental conditions. With this in view, we developed some acoustic sensor. In typically, the transduction principle used in acoustic sensor include that can be based on piezoelectric, piezoresistive, or capacitance phenomena. What we have chosen is the principle of piezoelectric effect, carried out the development of for study of low-cost thin film acoustic sensor suitable for high-intensity sound up to a decibel of 150 dB. So, we developed the acoustic sensor based on piezoelectric thin film to convert acoustic signal into proportional electrical output. Advantages of using the piezoelectric transducer include ease of processing and robust design. Also, piezoelectric acoustic sensors which do not involve air gap are known to have most robust fabrication process than capacitive sensors. So, this is the schematic of the acoustic sensor that we developed. The body of the blue color, what is shown is a body of the acoustic sensor which is made of perspex material, which is electrically insulating, light and transparent, and it is very easy for machining. It's not very expensive. It's a very economical material. And what is shown on the lower side here, this is a metal diaphragm, stainless steel diaphragm, and what is shown in the yellow color, on the here is a piezoelectric thin film deposited by sputtering technique. On the top, there are metal electrodes to take electrical leads. So lower side from the metal diaphragm, one lead is taken, and the top metal electrode deposited on the piezoelectric thin film leads are taken out, and this is how the whole assembly look like photograph. And the diaphragm of this acoustic sensor is made of special quality stainless steel SS304L, which is low carbon content material, can be exposed to high temperature up to about 900 degrees Celsius, and it has got good elastic properties. Sorry, it's not moving, I think. Okay. So we have chosen zinc oxide as a good piezoelectric thin film as a sensing film for our acoustic sensor. And advantages include a better piezoelectric coupling compared to other non-ceramic material, greater flexibility of its external phase, and it is a compositionally simple piezoelectric material which can be sputtered as a good piezoelectric film on a variety of substrate, including stainless steel. Okay, so there are a number of parameters in the sputtering process which need to be optimized. So what the technique that we used is called DC reactive magnetron sputtering. Sputtering was done in the presence of oxygen and argon gas. These are various parameters in sputtering like base pressure, working pressure, the combination of ratio of the argon and oxygen, target substrate separation, substrate temperature, many things. So in order to get a good piezoelectric zinc oxide, all these parameters need to be optimized. So this optimization was done by my student. These are the optimized parameters. So, and again, after the preparation of zinc oxide film, in order to make sure that it is piezoelectric in nature, we have characterized by some indirect method like X-ray diffraction, photometry method, etc., which gives an idea whether the deposited film is piezoelectric or not. These are the indirect methods. There is also a direct method called cantilever technique. This is a simple technique. What we have done is the zinc oxide film was deposited in a cantilever strip. Sorry, the pointer is not working. This is a stainless steel strip onto which we deposited the piezoelectric thin film, zinc oxide film, and on top of it, we deposited the metal electrode and leads were taken out, and this was connected to the oscilloscope. So when we subject it to mechanical deformation, this cantilever beam is subjected to mechanical deformation. If the deposited film is piezoelectric, the charge, it develops a charge gets converted onto the voltage, which can be seen on the oscilloscope. That's what this is a simple experiment that we did. So this is a schematic of the arrangement that we use. So what is shown here, this is a strip onto which zinc oxide film is deposited, and this is the arrangement to deflect the cantilever beam. It will attract when it is energized. When we remove the potential for this one, so it releases, so cantilever beam starts vibrating. So if the deposited film is piezoelectric in nature, so charges will develop and we get a corresponding voltage in the oscilloscope. That's what it is shown here. Yeah, I think this is not so clear. So this output signal that we get can be seen on the oscilloscope. This is the case on the top side when the cantilever starts vibrating initially from the upward direction, or otherwise depending on the signal that we get on the lower side. So of course this the amplitude decays with time, but however we can make out whether the deposited film is piezoelectric in nature or not. After the confirmation of this, we tried different substrates. In addition to stainless steel, we tried phenox, aluminum strip, Kapton, and mylar. We got a very good response with the phenox, which is a very flexible material with a good elastic property. There are some of the output signals that we could record. Then this zinc oxide thin film with optimized parameter was deposited into polished circular diaphragms. Subsequently, silver electrode deposition was carried out onto zinc oxide thin film, resulting in the MIM structure, metal insulator metal configuration. The top electrode was patterned in a later phase of experiment in order to improve the sensitivity of the acoustic sensor, and we found that segmenting the electrode enhances sensitivity, and necessary stress and strain distribution analysis on the diaphragm was done using a SANSYS simulation studies. These are some of the simulation studies that we did to have an idea about the distribution of stress. This is a deflection of the diaphragm. So this gives some idea about the distribution of electrode arrangement for this one, and we used this data. And then the performance study of this acoustic sensor was done using the acoustic calibrator. This was available at NAL, National Aerospace Laboratories. So the output characteristic that we studied include frequency response, linearity, and sensitivity. These are some of the responses that we got, the variation of the output response with the frequency. Now, some of the details like diaphragm thickness of 40 micrometer, diaphragm diameter about 1.5 centimeter. These are non-patterned, and these are the output that we got for different decibel sound pressure levels. 120 dB now, which is shown in the dark color, other one 130 and 40. So you can see that the response is almost flat, uniform. So, and then we also did this with a segmented arrangement, electrode arrangement, and we got an enhancement of signal of about 30%. So this is a comparison of the same. I will not go into the detail. What we found was that patterning the electrode suitably results in improvement of sensor response by about 35%. So the acoustic sensor developed to exhibit nearly flat frequency response and linearity up to 150 dB sound pressure level. In comparison with the general acoustic sensor, the presently developed acoustic sensor is attractive in view of low cost, less weight, and similar fabrication method. While it is low cost, it can be used as a disposable type sensor in case of its use in hazardous and radiation environments, as well as in biological applications. In fact, the same kind of the piezoelectric thin film, if we use on a silicon substrate, and we can make a MEMS-based acoustic sensor, which is very much there in the market. So with this, I will move on to another type of sensor that we developed using a piezoelectric thin film, that is impact sensor. Impact is a short period force, and it is expected that sensor for impact should have a fast response, and impact sensors are needed in several areas of science and engineering. So typical application of impact sensor include automobiles, aircraft. In defense also they are useful, railways, moon mission studies, oceanography, material testing, etc. So what we have done is the following. This is a prototype schematic showing the prototype of the impact sensor that we developed. It essentially involves a simple mechanical assembly consisting of a mechanical cantilever sensing element with a piezoelectric thin film fixed inside a round-shaped flexible enclosure and sealed to form an impact sensor. This is a rubber ball cut into two halves. So in one half, the cantilever beam is mounted and it is closed like this, and the leads are taken out. So if you do so, and necessary, the charge amplifier was also made by my student. This is a charge amplifier circuitry, and the ball that is shown is an impact sensor, this one. So in order to study this response, we have used a load cell. What we have done is this impact sensor dropped from different heights to make an impact with the load cell plate, and the response was recorded. It's a simple arrangement made in the laboratory, and some of the response that we got is shown here. See, when the impact sensor make a first impact, this is the maximum amplitude that we get. The signal decays and it rebounces, making a second impact. Compared to the magnitude of the first impact signal, this is lower, and it comes down with a subsequent impact, third, fourth, etc. So by analyzing the signal that we get like this, depending on the frequency, the magnitude of the first impact, second impact, the time, the gap between the first impact and the second impact, etc., we can make a careful analysis and get an information about the impact of the sensor with the body which it makes. So this is very useful in structural engineering, component design, etc. And another typical application of this is the following. What we done is we took a circularly shaped diaphragm like this, the base circular diaphragm, onto which what is shown in the green color is the piezoelectric thin film. On top again a metal electrode. So leads were attached, one on the diaphragm, another on the top electrode, and using this we made another type of sensor. This is how the exploded view of the sensor that we made. This is the HDPE housing that we made. This is a diaphragm onto which we form the piezoelectric thin film. These are all the sub-assemblies. When you assemble together, it looks like this. This is a exploded view of various subcomponents and final assembled view of the packaged impact sensor. This is for a different application. This is now the cross-sectional view of the sensor, and this is a photograph of this. So I have shown a coin by the side of the photograph of this assembled impact sensor to get an idea about the overall size of this one. So the response of this sensor we studied using an arrangement like this. The sensor is located here. This is the sensor. This is a glass tube, and this is the power supply with an amplifier circuitry. The output is connected with an oscilloscope. What we have done is we took the rubber ball, the metal ball, and another plastic ball, and dropped these balls from different heights onto to make an impact with the sensor, and we recorded the output signal. So what we done, we took iron ball and a glass ball and a ball made of wood and a plastic with a different densities, of course, with the same diameter. So each one of them were dropped from different heights. Glass tube acts as a guiding tube actually. So when they're dropped from different heights, they make a collision with the impact sensor. The response was recorded. So some of the data that we got was now plotted here. This is the drop height versus the impact force in millinewton, and then the corresponding the data for each one of them is shown. I will not go into the detail. Just of course, these are all the materials engineering part, which the zinc oxide thin structure was analyzed using SCM analysis, etc. And then of course some more data about each one of the. This is the case with the iron ball dropped from different heights, and this is the maximum amplitude for the first impact, second impact, and like that. So when we drop the same ball of same diameter, they made of glass, the typical data. So detailed analysis was done with the signal that we got. I will not go into the details. Then we calculated the drop height versus the output voltage, and then the network done, etc. These are very useful to analyze and get an information about the kind of impact it makes and the material with. So suppose there is a material which is not known as unknown material. By having this kind of best fit data, we can also find out the unknown material which makes an impact with the. So these are some of the further study. The another very interesting application of this impact sensor that we made by my students is that especially in milk adulteration or adulteration, the drug, etc. So what we had done is we took a syringe in which they either milk, pure milk or whatever it is. So it was made to drop onto the impact sensor by drop. So when you get the signal, we can analyze. For example, this is a pure milk signal, what is shown in the black color. Any adulterated is kind of, although it may not give a immediate, but by effect this thing we can make out is a pure or impure. Similarly, similar kind of thing can be adopted if there is a adulteration in the drug, for example. So these are some of the initial studies. More detailed this thing, the analysis is done. I think.
How long does it take to do this experiment?
It's just take the liquid in the syringe and just drop it. You get that signal. Yeah, it's a simple setup. There's a charge amplifier and the output voltage you are seeing on the oscilloscope. So for a quick check. Okay. So then piezoelectric thin film array for monitoring the impact events, etc. This is a little bit similar to this thing. I think because of lack of time, I think skip this. And then we also done the development of MEMS space sensor. The advantage of MEMS space sensor, the miniaturization and less weight, fabrication and less mass production, low cost, improved performance, reliability, because miniaturization has become the order of the day. Everywhere, reduction of size. The best example that I give is a mobile phone. Although people used to have a land phone, now they're almost outdated. But similar thing is happening in sensor technology. Whatever it was available in the bulk, people want to develop using a miniature version, wherein MEMS technology is very important. MEMS stands for micro electromechanical system. It has both mechanical components and electrical components. So we did some work on this one. So I thought of taking an example of a pressure transducer, which is basically electromechanical system, which is useful in measurement of pressure in process industries, automobile engine, depth study, oceanography in many areas, including biomedical area. These are some of the pressure sensor that we developed. The earliest one using a metal diaphragm, which did for space application. These are the strain gauges that we deposited into technology. And this is a complete assembly. This is only the diaphragm part. When you assemble together with other parts, it appears like this. Then we extended this using silicon technology, miniature version. This is how it looks like this. I will not go into details because of the limitation of time. These are there are different processes involved. The most commonly used process is called bulk micromachining process, which will have so many steps: deposition of insulating layer, patterning, etc. And finally, vapor bonding, attaching leads, dry etching, all those things. Because of the limitation of time, I'll skip this. And this is how the cross-sectional view look like this. So these are the cutout portion. On the top, we have the thin film strain gauges, which are connected in the Wishbone bit configuration. This is fully made active, gloss to metal sealing, and then finally packaging. Packaging is a very important step. So by suitable packaging process, we can make the pressure sensor either as an absolute type or a relative type or a differential type. Suppose if a pressure transducer measure pressure with respect to vacuum, we call it as a absolute type pressure. It measures the absolute type pressure transducer. So suppose your pressure transducer measure pressure with respect to local atmosphere, then we call it as a relative type pressure transducer. Most of the biomedical type of pressure transducer that we see in the hospital, or relative type or a gauge type pressure transducer. Sometime one will not be interested in measuring the absolute or relative type, but one will be interested in knowing the difference between two unknown pressures, say P1 and P2. In that case, we call it as, if the pressure transducer gives an indication of the difference between the two unknown pressure P1 and P2, it is called a differential type pressure transducer. Depending on finally how we do the packaging, we can make it as either an absolute type or a relative type or a differential type. So in fact, all the 3 types we could realize. Lastly, I thought I will touch upon MEMS-based piezoelectric microjet, which has several applications. Maybe another 1 or 2 minutes I can take. Oh. So this is the silicon-based technology where we have 2 diaphragms. This is one part, lower part, onto which we deposited piezoelectric thin film sandwiched between 2 metal layers. On the top is a silicon diaphragm with a small hole of the order of 2 microns. So both these diaphragm of fabrication, they bonded. This is an interface. So this one, this is here actually the piezoelectric thin film, piezoelectric material that you deposited is used not as a sensor but as an actuator. In the beginning, I mentioned that now we need both sensors and actuator. In this, when you subject it to electrical potential, when you apply the piezoelectric material, it deforms. So this deforms make this silicon diaphragm to go undergo some compression or this one. So this kind of this one, what it does is, let us say this small volume which is formed due to the bonding of the 2 silicon diaphragm is of the order of say few microliters or whatever it is. If you fill the liquid in this and then apply a potential for this thing, because of the minute deformation of the lower side thinner diaphragm, there will be a build-up of the pressure of this liquid and this gets thrown out. So this has the application as a microjet in drug delivery, etc. So one of my students is a sponsored candidate from IISc Chandigarh. He did this as a part of his PhD program, and this is how that we use the piezoelectric thin. These are some of the analysis that we did. This is silicon diaphragm onto which the initially piezoelectric crystal we used and tested the property of this actuation, and later we replaced with a thin film. And the performance was studied using a system laser vibrator arrangement which is available in our institute. This is a system. These are some of the data. Deflection measurement using laser vibrometer with a potential 60 volts and 10 kilohertz. And some more data. And there is an animation, I don't know whether it is works, etc. When you apply a potential, it starts like this. It starts moving up and down. Because of this minute up and down movement of the lower side silicon diaphragm, pressure of the liquid in this small volume increases and makes the liquid to throw out. So this has the application in controlled drug delivery in biomedical application, things like that. It also has many other things, something like this. So these are some of the responses at lower frequencies like 500 Hz. And on the top side diaphragm, which I mentioned that the holes of the order of few microns, this was done by laser drilling technique, which was available at Chandigarh. These are now of the order of 0.2 mm, that 0.1 mm. Depending on the type of liquid they want to jet, we can choose the different diameter for the holes in silicon diaphragm. These are some of the things that I said. Then, of course, lastly, I don't know whether I have time, piezoelectric nanogenerator also we developed. This was the PhD work of one of my students. Presently, he's at Korea. Nanorods that we use. Piezoelectric nanorods is an interesting this thing. Same material can be synthesized using thin film technique as either nanorods or nanoplates. We have synthesized the same zinc oxide as a nanorod. If the combination of thin film and other processes include. I will not go into this except that I will show the, these are some of the application of piezoelectric nanogenerator. Again, we used, there are different piezoelectric material, but since we had the experience of zinc oxide, we have chosen the same zinc oxide. And synthesis of zinc oxide we used by a hydrothermal method. Advantages I mentioned. These are the different steps that are needed. Substrate preparation and cleaning. Phenoxide used. Deposition of gold with a chromium back layer for adhesion. And then deposition of zinc oxide as a seed layer of 100 nanometer. And we synthesized by a controlled temperature process to grow nanorods, zinc oxide nanorods. How they look like, these are some of the process steps for the synthesis of zinc oxide nanorods. And these are the electron microscopy pictures, top side view of the nanorods, zinc oxide nanorods that you could synthesize. Some more data of the size and the length of the nanorod that we could electron microscopy pictures. There are various parameters we can optimize to get the required size of the nanorods of zinc oxide and their thing. So these are some of the optimized parameters. We analyzed using XRD, other thing, and we have used these zinc oxide nanorods to fabricate a generator. And these nanorods, when they synthesize, they become very delicate. So in order to make them robust, we filled with a polymer, PMMA, so that they become robust and strong. And the top side should be made reachable for the electrical conducting layer. Therefore, this top PMMA layer was removed by using called a dry etching technique. So that's how the top side look like this. And on the top side, we coated a metal gold electrode and formed a generator like this. So these are the nanorods, zinc oxide nanorods. On top side, we removed by dry etching technique. And again, we press this Kapton layer, deposited the gold to form a nano generator. So we took one lead from the bottom metal gold electrode and the top one here, and then we realized the nano generator. So there are some of the results that we got. I think there is also a video, and when we subjected to repeated impact, this is how the signal that we got. Maximum we could get about 0.93 volts. And there is a video, if time is there, I can show. This is how the, one second. So this is a small motor. So when it's energized, it starts rotating. This yellow curve, what is shown is a nano generator. So when it starts rotating, the projection of this motor keeps touching periodically, and we get an output from the nano generator. Let me see whether it works actually. Okay. Oh yeah, 1 second. It is setting the things. That's how. Leave it. This is the input power for the motor. On the oscilloscope, even everything, we have to set the gap between the the projection of the motor and other setting. So when everything is set, you can see the output from the nano generator. So he's setting the it starts rotating, and periodically it keeps touching the nano generator, and the voltage generated can be seen on the oscilloscope. Yeah. So you have to set the gap, etc. suitably. So this is how we get. This has the application in energy harvesting, especially that's how it does. So this is the work of one of my students. Presently is a postdoc at Korea. I think I will stop at this stage. I have few other things, but I thought as a sensor device, many of these youngsters will be interested. So I hope that it will inspire many students to take up the area of sensor as a research topic in their work. Yeah. Thank you. Thank you. If you have any questions, I will put you. Okay. Okay.
Any questions from the students?
Yeah.
Maybe we can talk to.
We can take the questions later.
Yeah.
The students
Okay.
during the lunchtime we can
Yeah. Okay.
with us. Thank you so much, sir.
Yeah.
for your
Okay. Thank you all for your
Because
patience. Yes.
because of time limitation.
Yeah. I understand. Yeah. Sure.
As long as it does not take a lot of time.
Okay.
Our next speaker is
Yeah.
just 1 minute. We will participate Professor Rajanna, and then